Hi, my name is Colin Murphy,
Hi, my name is Nishant,
and we're working with the Ames Housing Pricing Dataset. So a little bit of background before we get into this. As I'm sure many of you lived through, in 2008 we had a major financial crisis which led to the bursting of our first housing bubble in the United States. As a result of this, many private equity firms, such as BlackRock, have been purchasing up homes to turn into rental properties, taking them off the market and increasing the overall prices of houses in the United States. As such, many prospective first-time home buyers have found it difficult to both buy a home and determine which features are important in terms of making purchasing decisions. So our goal with this is to predict housing prices accurately, and noting that this is specifically related to Ames, Iowa houses and should be considered for any future predictive purposes. So the major issue that we encountered first was that since this was a Kaggle competition-based data set, while we first had a training and test split initially, our test data did not actually have a response variable, since this is mainly used for submission purposes. As such, we only had 1,460 final rows to actually work with and split into a training test split. So our initial assumption at the time of the starting of this course was between a linear or a polynomial model, that a polynomial model would most likely be better predictor in terms of predicting housing prices in Ames, Iowa. So going over the data set. Of the total features, we have 79 total features with one response. 24 of them are numeric in nature. 35 of them we flagged as potentially being ordinal categorical variables, and 20 of them being nominal categorical variables. As you can see, we have a large number of features that are categorical in nature, and this was something we needed to consider going forward. As previously mentioned though, this is specifically limited to Ames, Iowa in terms of the data set that was used to train it, and should be considered for any predictive purposes in any other locations. So our next major concern that we encountered was during our data pre-processing step, we wanted to see if there are any missing values in our columns. As such, we found a fairly large number of columns with missing values, some of which even having missing values exceeding 50%, which is a major red flag for us. As such, we needed to take a step back and determine what might potentially be causing this. So after taking a step back, we reviewed both the raw CSV file as well as the Kaggle data dictionary, and managed to find that there are a large number of columns in the data set which had NA as categorical columns, or categorical values for their columns, which as a result meant that Python was innately handling them as missing or not available values, which needed to be changed. So we changed our import schema, which accounted for this, and as a result, only ended up with 3 columns that had missing values, those being lot frontage, garage year built, and masonry veneer area. Next, we needed to determine what we would do with these columns. In order to determine this, we had to use a correlation plot against our actual response variable, since they are numeric columns in nature. And as a result, all of them showed to be having correlation coefficients of less than 0.5, meaning that they likely were not relevant predictors to begin with. This, combined with the fact that some of these columns are related to other columns, meaning imputing them wouldn't potentially be accurate. For example, garage year built is impacted by other garage columns, such as garage car size, which garage car size has no garage as an option, meaning if we attempted to impute a missing value for garage year, for a garage or for a house that did not have a garage, that wouldn't be relevant. So we decided to drop these 3 features. So as previously mentioned, one of our major problems was that we had way too many categorical features, which if we attempted to one-hot encode all of them would drastically increase the amount of total features present and increase the amount of time it would take to train our models. As a result, we went with ordinal encoding for as many features as appropriate, meaning we had to go through our data dictionary for all 79 of our features and determine 1, if it was categorical, and 2, if it could be ordinally encoded. Some examples of these being columns that have innate order present in them, such as pool quality, having the best related score of excellent and a lower one of fair, to not having a pool at all being the lowest potential score. Next, for time-based columns, we needed to actually encode these as categorical features, and in order to do so, we conducted histogram plots with kernel density estimation lines. The reason we did this is that kernel density estimation lines gave us a rough idea of how the data itself was distributed, which we could then use for quantile bagging to turn these into bagged columns for specific date ranges, and then limit the number of levels to that ordinal column. As you can see here, for the year built, there are 3 potential peaks in the kernel density estimation line, and as a result, we did a quantile split of 3 against this and ended up with 3 distinct categories, which had roughly a 33% or perfectly even distribution across all of them. And we did this for the remainder of the columns that were similar to this. As a result of all of this initial pre-processing, we set up a column transformer inside of a scikit-learn pipeline in order to streamline our process, in which we did standard scaling for all of our numeric columns in order to ensure that they were more evenly distributed and wouldn't overestimate certain features with larger standard deviations. And then for any nominal columns, we would one-hot encode them and then perform a manual setup for our ordinal columns, in which we encoded them by hand using a mapping schema in order to do this. So for feature selection, at first we had worked with all of our features, which was 192 after encoding, which managed to make all of our models take a long time to run, but had also led to us not be able to use data frames after our transformation pipeline. The reason for this is that because of the number of one-hot encoded variables that we had, this led to us having a very sparse matrix with zeros, and encoding it into a data frame schema meant that we would have a loss of information, which caused all of our models to fail, unfortunately. So we had to perform feature selection, not only to bring us down from 192 total features, but to also try to improve our total model performance. We attempted to do so using a number of different approaches. Prior to us actually learning PCA, we utilized the primary underlying calculations of eigenvectors and eigenvalues to determine which features were related to the largest amount of variance within the feature set, not necessarily related to the actual response. That one did not perform well. We then attempted random forest feature importance, which brought the number of features down too much, so to roughly 30. Our best performing one was actually a lasso CV regression, which brought us down from 192 to 74 features. That's roughly 38% of our original features.
Okay, so moving further with the linear model. We did the linear model. At first, in our linear model, we decided to use stat models so that we could determine statistical significance for our predictors. Our linear model had an adjusted R-squared of 0.866, which means that it explains over 86% of variation in sales prices of homes due to our 74 features. For example, the column at the bottom, nominal neighborhood, is Crawford. A home being in the Crawford neighborhood increases the potential sales price of the home by $20,450, holding all else constants. So, however, we wanted to make sure that it was even valid for us to use a linear model on our data. We generated a residual versus fit and normal QQ plot to determine this, as you can see in the picture. Given the residual versus fit output, the residual show a non-random distribution, potentially even a quadratic distribution. Thus, the residuals are not independent and homogeneous. Given the QQ plot output, in which either end of the lines deviated from the line, indicating the residuals are skewed on either end. So both of the plots shows the ordinal least squares may not be appropriate. So moving further, the models that we evaluated were first of all we did the lassos and ridge regression, as well as to see if either penalty terms improved the linear model results further. We did 3 different degrees of polynomial regression: 2nd degree, 3rd degree, and 4th degree. We did 3 different decision trees, one in which we did a grid search for all minimum features and leaf size, one of max depth search, and our last one being a cost complexity prune tree. So moving further, we also did bag tree and random forest models. So we initially thought we would choose neural networks as our self-taught model, but it was too hard to tune with a horrible RSME of almost 200,000, so we couldn't do it. So later we choose to do extreme gradient boosting model instead, so which gave us a better result. So moving further, talking about the hyperparameter tuning, since many of our models utilize grid search CV, we experimented with many different hyperparameters and valued for them. For example, XGBoost, we tested different learning rates, max depths, gamma, and alpha. So moving further, what was our major roadblock and what were the conflicting results? Our most concerned roadblock we encountered was our initial model results. Our best performing model up to this point tend to have lower bias, which also mitigated variance, which is XGBoost and random forest. However, our linear model was outperforming polynomial, which linear models are inherent susceptibility to bias. So polynomial models tends to have higher variance but lower bias compared to the linear ones, as you can see in the results in the picture. So moving further for the RMSE results, as a result, we tried applying different linear regression involving penalty terms. We ended up setting on using a rich CV regression with alpha grid, which shot our quadratic, which is polynomial 2 model up in the second phase, up in the second place. So moving further, so all this I want to conclude is that while we were somewhat correct in the polynomial of which is degree 2, outperformed linear regression, but unfortunately it did not perform the best. So the XGBoost, we are well known for a great performing enables tree model and similar to polynomial models, reducing the bias. As such, the order of the final results makes sense. So therefore, our dataset benefits from more complex models that we also serve to reduce bias. So one last thing, we were not able to give a live demonstration. Some of our models take 30 minutes to run on their own. So our total run time is over 85 minutes, so we didn't perform the live demo. Yeah, thank you.
Thank you.
One last few points I would like to mention is, first, there were some interesting findings related to what features our tree-based models determine to be important. As you can see, all of our trees that are decorrelated, as in our back tree model and three decision tree, they all return very much similar feature importance, with live grid area, which is above ground living areas square feet, garbage area, and total basement square feet being consistently the third most important feature, which makes sense. Who would want to be a bigger garage and more total housing space? So next, as for our more advanced assemble tree, both still choose grill live area, which is above ground living square feet, to be the most important, but our best model, which is XGBoost, found that the foundation category of poured concrete was apparently very impactful in determining the final sales price, along with the additional feature difference. As you can see, bagging and boosting uh, ensembles method both have their pros and cons, but for our goal of lowering bias, boosting clearly is the most important for us. So one more point I would like to add, for the initial assumptions we did for our polynomial model. So to summarize, our best performing polynomial model and the second best model overall, the second degree one using rich CV regression yielded the following coefficients, as you can see in the slide. Several features substantially impacted house sales price. For example, every square foot increased in above ground living area. The sales price of a home increased by $4,093.30, holding all the else constant. Another key finding is the role of interaction terms. For instance, in the North Ridge Heights neighborhood, every additional square foot of basement space increased the effect on sales price by $4,835.69 compared to the house areas in the other neighborhoods. That's it about this slide. Thank you.